Hello everyone, welcome back to the Chemical Engineering and Aspen channel. And as you know, these days we are focusing on the module of Chemical Reaction Engineering. And in this regard, we are bringing the lecture number 13 for our valuable viewers. So from this lecture, we will move to the building block number 3, which is stoichiometry. In the first 12 lectures, we have covered the building block number 1, which is mole balance, building block number 2, which is rate law, and now our next few lectures will be on stoichiometry, which is building block number 3, before moving to the isothermal design, which is building block number 4. So in today's lecture, we will first develop a stoichiometry table for batch system, then we will derive the concentration terms for the batch systems, and then we will solve an example. So looking at the batch system, at time t is equal to 0, the number of moles of A are Na naught, for B Nb naught, for C Nc naught, Nd naught, and for inert it is I naught. We have considered, as we have seen before, that A and B are reactants in the system, while C and D are products in the system. After some time t in this batch reactor, the final number of moles are Na, initial number of moles were Na naught, final number of moles are Na. We will represent, or our nomenclature will be, that once we denote naught, it will be for the initial, and once we do not denote it, like we say Na naught, it is for initial number of moles of A or moles of A at the inlet of the reactor, while Na means moles of A at the outlet of the reactor. We will use the same nomenclature for the flow rate, that if we say Fa naught, that is the flow rate of A at the inlet of the reactor, and similarly Fa, that is the outlet of the reactor. Similarly, Nb naught is converted to Nb, Nc naught to Nc, Nd naught to Nd, and Ni naught to Ni. So we have seen the reaction A plus B over A into B, C over A into C plus D over A into D. And you have seen in the previous lectures as well that we have divided by the stoichiometric coefficient of the limiting reactor, which was A in the system. And accordingly, we have seen the expression Na is equal to Na naught minus Na naught x. We had derived that expression in chapter number 2, and we had said that Na, the number of moles of A after the reaction or at the outlet of the reactor, is equal to initial number of moles multiplied by 1 minus the conversion in the system. The more the conversion, the more will be the reaction in the system, and lesser will be the number of moles of A. The lesser the conversion, the more will be the moles of A at the outlet of the system. So developing the stoichiometry table, first we have to specify the species. There are 5 species in the system: A, B, C, D, and I. A and B are reactants, C and D are products, and I is the inert in the system. The initial number of moles are Na naught, Nb naught, Nc naught, Nd naught, Ni naught, respectively for each species, and the total number of moles will be the sum of these 5, which is Na naught plus Nb naught plus Nc naught plus Nd naught plus Ni naught, so that is equal to Nt naught, the total number of moles at the inlet of the reactor or at the initial condition. Then we have to specify the change. The change will be minus Na naught x for this species A. For species B, it will also be negative sign because it is a reactant in the system, but now it is multiplied by its stoichiometric coefficient, which is B over A, as we have seen. Similarly, for C, which is the product in the system, it will be plus C over A into Na naught x, because A is the limiting reactor. So accordingly, the initial number of moles of A multiplied by the conversion and then multiplied by the stoichiometric coefficient in the balance equation, after dividing by the stoichiometric coefficient of limiting reactant and making the stoichiometric coefficient of limiting reactant as 1. Similarly, D over A into Na naught x, while there will be no change in the inert. That is why it is called as the inert in the system. Now once we add up these, the Na is equal to Na naught minus Na naught x. Similarly, Nb will be Nb naught minus B over A into Na naught x, as you can see here. Similarly, Nc will be Nc naught plus C over A into Na naught x. Nd naught plus D over A into Na naught x is equal to N of D, which is the number of moles of D at the outlet of the reactor, and Ni, the number of moles of inert, will be the same as that of the inlet. So that will be Ni naught. So once we sum up all of these, Na naught, Nb naught, Nc naught, Nd naught, and Ni naught, these will become as Nt naught, as we have seen here. So this term will come out here. Then if you see the second term of these, then you can see that Na naught x is a common term, while minus 1 minus B over A plus C over A and plus d over a terms are involved here. So you can see that this expression is derived over here, that this part is converted to n t naught, while the remaining part, this one, as you can see here, is converted to this one. N a naught x is common among these, so minus 1, which is this one, minus b over a, plus c over a, and plus d over a. And the terms in the bracket are converted to a parameter which is we call it the sigma, which is the change in total number of moles divided by the moles of A reacted. So accordingly, the total number of moles at the outlet of the reactor will be equal to total number of moles at the inlet plus Na naught x multiplied by this factor sigma, and sigma is equal to change in total number of moles divided by the moles of A reactor. Now we will derive the concentration term for the batch system. We know that C of A, or the concentration, is equal to number of moles divided by the volume of the reactor. Similarly, we know Na is equal to Na naught into 1 minus x. So what we will do, we will put value of Na over here, and that will be Ca is equal to Na naught 1 minus x over V. For Cb, Nb over V, and the value of Nb is Nb naught minus B over A into Na naught x. We have derived that expression in the stoichiometry table. For C of C, Nc is equal to Nc naught plus C over A Na naught x over V. And for D, same case, Nd naught plus D over A Na naught x over V. Now for the batch reactors, we see that these are the solid vessels. So the reactor volume will remain the constant, which means that this V will become equal to V naught, and once it will become equal to V naught, that Na naught over V naught, what it will become as Ca naught. So that you can see here as well, that at Na naught over V naught has become equal to Ca naught. Similarly, as you can see here, that Ca is equal to Na over V. So once there will be naught, there will be naught, so accordingly that will be Ca naught. So Ca is equal to Ca naught into 1 minus x, and we have seen that expression in our chapter number 2 as well, where we had derived it. Now for Cb is equal to Nb over V, Nb naught minus B over A, Na naught x over V. Now how to write these expression in that case now? What we need to do? We need to first see a correlation. Theta I is equal to moles of species I initially over moles of species A initially. So how it will be turned? That for example, theta I is equal to Ni naught over Na naught, or Ci naught, the concentration of that species at the inlet or initially, over the concentration of the limiting reactant initially, or Yi naught, the mole fraction of that species initially over mole fraction of the limiting reactant initially. So what it will be do, how we can transform it? We can take Na naught common from this expression. So what it will become once we take Na naught common from here, that will be Nb naught over Ni naught minus B over A into x. Now this Nb naught over Ni naught, as per this definition, if you see here, will become as theta B minus B over A x over V naught. Now this Na naught over V naught will transform into Cb is equal to Ca naught theta B minus B over A into x. The concept is very simple. You have to first take the number of moles of the limiting reactant out of the equation, or you have to take common from here. Here it was not present, so obviously it will be divided here, which is Nb naught over Na naught minus B over A into x. This Nb naught over Na naught, as per this definition, is converted to theta. So for this B, it will be theta B. And this Na naught over V naught from outside the bracket will be converted to Ca naught. So Cb is equal to Ca naught theta B minus B over A into x. Similarly for C of C, it will be Ca naught theta B will be replaced by theta C. Here it was minus B over A, here it is plus C over A. And same will be the case for C of D, that Ca naught theta D plus D over A into x. So these are the concentration terms. So we have derived our first two parts. First part was the stoichiometry table. As you have seen, we have drawn that table. As you can see here, that we had derived that stoichiometry table, and then we have derived the concentration terms for A, B, C and D. Now to summarize it, that 1 mole of A plus B over A into B, C over A into C plus D over A into D. To summarize, for the constant volume system and for liquid phase reaction, we can say, and we can use the rate law, that minus Ra is equal to KCA CB, and Ca has gone to Ca naught into 1 minus x, while Cb is equal to Ca naught into theta b minus b over x. Now that C of b contains Ca naught, C of a contains Ca naught, so that will be Ca naught square. So K Ca naught square 1 minus x theta b minus b over a into x, and now you can see that the rate of reaction is a function of conversion for the system. We had to come to stoichiometry. If it was simply minus R is equal to Kca always, then we do not have to go to the stoichiometry every time. We can simply say minus R is equal to Kca, and that is equal to Kca naught 1 minus x. But now it involves B, and even it could involve C, D as well. So accordingly, we had to always write the concentration or derive concentration terms for the other species in the system as well. And then we had to write the rate law for the system. So you can see that for Ca it was Ca naught into 1 minus x, for Cb it was Ca naught into this factor, so Ca naught square 1 minus x theta b minus b over a. And we have seen that how rate of reaction is a function of conversion. Now we will solve this example. I will skip the stoichiometric part and will move on to the main part over here. We will simply say here that the soap consists of sodium and potassium salts of various fatty acids such as oleic, stearic, palmitic, lauric and majestic acids. And you can see the reaction that 3 moles of sodium hydroxide plus 1 mole of this produces 3 moles of this and 1 mole of this. So we are assuming that this sodium hydroxide is the limiting reactant. So if it is a limiting reactant, then its stoichiometric coefficient should be 1. So what we need to do, we need to divide this whole equation by 3. So what it will become, A plus 1 by 3 B goes to C plus 1 by 3 into D. Now if you see the stoichiometric table which we have to prepare initially, this is A, B, C, D and water is inert in the system. So Na naught, Nb naught, Nc naught, Nd naught and Ni naught, this all will become as Nt naught. For change, it will be minus Na naught x, it will be minus 1 over 3 minus b over a, so it is minus 1 over 3 Na naught x C over a, where it is 1, and D over a, which is 1 over 3 Na naught x. So once we sum up all this will be cancelled out with this will be cancelled out with this, so change is 0 over here if we sum total change. So once we add up these, Na is equal to Na naught into 1 minus x, Nb is equal to Na naught theta b minus x over 3. We have just derived the concentration term. Now you can understand that how it has become. Nc is equal to Na naught theta c plus x, and Nd is equal to Na naught theta d plus x over 3. Now this minus x over 3 will cancel out with this x over 3. This x will be cancelled out with this x. So accordingly, the Nt is equal to Nt naught in the system. In the same case, dividing by V naught, we get Ca naught 1 minus x. This Na naught is converted to Ca naught theta b minus x over 3. This will be Ca naught theta c plus x, and this will be Ca naught theta d plus x over 3, and this will be Ci naught. So these are the stoichiometric table and concentration terms derived over here. But now in our second part, we have to see whether we have chosen the right limiting reactant or not in the system. Having set up the stoichiometric table in the previous slide, we can use it to calculate the concentrations and the given conversion. Now if we assume that the initial concentration of sodium hydroxide in the system is 10 mole per cubic decimeter or 10 mole per liter or 10 kmol per cubic meter, and glycerol rate at a concentration of 2 mole per cubic decimeter, that the concentration of B is, initial concentration actually, is 2 mole per cubic decimeter while that of A is 10 mole per cubic decimeter. What are the concentrations of B and D, like the species B which is the reactant and species D which is the product, if the conversion of the limiting reactant is 20% and 90%? We will see whether we have chosen the right limiting reactant or not. Now, if you see that only the reactants are present in the system, it means that theta C, now what is theta C? Nc naught over Na naught. If there is no C present in the system, then what will be the value of Nc naught? It will be 0. So theta C will be 0, accordingly theta D will be 0. So what we come up with, take you back, that is equal to C of D is equal to Ca naught theta D plus x over 3. Now this theta D is 0. So what it will become? Ca naught x over 3. Now Ca naught is 10, x is 0.2 over 3, so that is 0.67 mole per liter or mole per cubic decimeter. For Cb we know Ca naught theta b minus x over 3. We have been given that Ca naught, the value of Ca naught is 10 mole per cubic decimeter. Theta b, what is theta b? Nb naught over Na naught, or in other words we can say Cb naught over Ca naught. So Cb naught is 2, Ca naught is 10. So 2 over 10 minus x over 3. What is x? 20%, 0.2 over 3. So it comes out to be 1.33 mole per cubic decimeter. So we can say by here that we have selected the right limiting reactant. But now we'll move on to the next part, which is the 90% conversion of NaOH. Now CD is equal to Ca naught x over 3. Ca naught again is 10. X is now 0.9. So once you divide it, you get answer of 3 mole per cubic decimeter of D. However, once you go to Cb, that is Ca naught theta b minus x over 3, 10, which is Ca naught, Cb naught over Ca naught, 2 over 10 minus 0.9 over 3. So the answer is negative, minus 1 mole per cubic decimeter. Now, why this negative sign has come? It is impossible that the concentration could be negative. Then why it has come? Because we have selected the wrong limiting reactant in the system. If we had selected the glycerol stearate as the limiting reactant in the system, then this answer would have been positive in the system. It means that we cannot simply or blindly choose one reactant as limiting. We have to do the calculations and we have to see that all the values of conversion, the answer of the other species doesn't go negative. So that is the true representation of how to choose a limiting reactant in a system, and you have to choose it very carefully, because then the design, which is the isothermal design or adiabatic design, will depend on your stoichiometry assumptions. So that's it from today's lecture. I hope you have enjoyed the lecture. We have covered a major part of chapter number 4 here, that we have developed the stoichiometry table, we have developed the concentration terms, and we have solved an example for the batch system. If you understand it correctly, then the flow system will be very simple, which we will be solving in our next lecture. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video, and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.